please.
Hi, Sean.
Hi, Sean.
Hi, Sean.
Hi, Sean.
I'm sorry, Sean.
Okay, the cross product. It's been mentioned in physics.
That's it.
Yeah.
Music. Right here. Oh, that was.
Okay.
I'm not in crew. Or if you're working with electrons.
So when we multiply two vectors using the dot product, we get a
Scalar.
yes. Multiplying two vectors with the cross product will give us a vector. Let's go back to determinants for a moment. Matrices.
Exactly. Oh, that's where these come.
2 by 2 matrix, those vertical bars mean determinant. Do you remember how to find the determinant of a 2 by 2?
Yes. It's annoying, but E, B, C,
AD plus BC.
Chris minus cross.
Wait.
No.
Oh.
And then you had to like encrypt your names.
You learned this from me.
Okay, that's what I thought.
Oh, you do
I thought that
diagonals.
was also.
Okay, a 3 by 3 matrix. Recopy
And do diagonals.
the two columns. And now we're going to have 3 diagonals minus 3 diagonals. Okay, so we'll have AEI plus BFG plus CDH. And then we're going to have to subtract all of the up diagonals. GEC, HFA, IDB. So it's still the concept of Chris minus cross, but on a larger scale. Okay, this is notation for cross product. We read this as U cross V. Okay. If we're taking U cross V, our first row of our matrix is I, J, K. The second row of our matrix is vector U. The third row is vector V. And then we find the determinant. Chris minus cross.
That's still a single number.
What?
Maybe the determinant is still a single number.
No, the terms of IJK.
Right. Since that first row is IJK, it will be in terms of IJK. So for example,
Could you sign this really quick? It's for, I'm gonna be gone.
Oh, wait,
Just for
don't
four
want to
times.
go through?
Are you on a filter thing?
I haven't.
That's what I'm getting done right now.
oops,
You think it'll be fine?
I signed on the wrong one.
That's no problem.
You going?
That's what you make out of it, Kathy.
Okay.
So our example,
I can sign up.
I want the cross product between 2, 3, -5, and 1, -2, 3. So for U cross V, our first row is I, J, K, and then we're going to fill in vector U and vector V. So, copy the first two columns. Now we gotta do Chris minus Chris. So, first diagonal, I times 3 times 3. Plus J times -5 times 1. Plus K times 2 times -2. Huh?
I just said the resolution on it is 4K.
Minus 3K plus 10I plus 6J. So what is our resulting vector?
-1, -11, -7.
So negative I minus 11J minus 7K. I would like you to take a moment and find me V cross W.
We cross W?
Yeah.
V cross U.
Ah, V cross U.
Okay. These are gonna be different.
They're gonna be anti-parallel.
It's
not
gonna
gonna be like
that, but opposite. Hey, I got it right.
I didn't say anybody was right.
Is that right? Because that was on the
No, I was just showing her. Okay, turn to your neighbor and compare your answer.
What you get? Neighbor?
Something wrong, I think.
Oh, neighbor.
What you get?
Oh, John, that's right. Negative thing, times another negative thing. It's the same vector, they're just moving in different directions. That would be a 50.
Yeah, I think that actually
All right, what do we get?
5 plus 11 J plus 7K.
Oh, that's got it.
So what is true about U cross V and V cross U?
They are parallel.
And
U cross U equals negative B cross U.
Which does mean they are parallel, right? Because they're scalar multiples of each other. Okay. Pod 1. I would like you to take U dot U cross V.
4.
Pod 2, I would like you to take the dot product of V and U cross V. Pod 4,
yeah.
U dot V cross U.
B cross Snap, son. Thank you.
Yes, Father. I'm sure I feel like that.
Okay, pod 1.
0.
Pod 2. Pod 4.
Follow the pattern.
What's the
Well, we don't know.
I think the pattern
I thought we
would
need like
be
4 terms.
What's true about U and V and the cross product? Thank you. There are orthogonal. U, V, U cross V is orthogonal to U and V. Hence your right-hand rule, whatever it is. Okay. Now let's stick with this same example of these two vectors. I want to find the angle in between them. Cosine of theta is the dot product over their magnitudes. Okay? So let's go back up to dot product. 2 minus 6 minus 15 would be negative 19. Magnitude of U would be 4 plus 9 plus 25.
78.
And magnitude of V, 1 plus 4 plus 9.
without a calculator.
Okay.
Oh, that's out. Not done with that.
145. It's an error.
Still not done.
It's because it's a line.
0.4602. You're too slow.
Yeah.
Okay. The magnitude of U, we decided was radical 38. The magnitude of V, we decided was radical 14. What about the magnitude of the cross product?
What's this one?
160.
171. It's
121, yes.
121 plus 49 plus
No.
1. Okay. So
There's no relationship.
Or is there?
or is there? approximate the square root of 171 for me on your calculator.
13.077.
Okay, keep it there. Now take radical 38 times radical 14 times the sine of 145.462.
Well, I feel like we're the same. It should just
Nothing happens.
Whoa!
It's like 1 plus 2 equals 1.
145.462.
Whoa.
Well, they are equal, but you rounded your equal.
Yeah.
Okay. So.
Problem.
Some very specific
I was
scenario.
gonna say, we will have home.
Nope.
Yeah, there's no homework.
Sorry.
No.
Oh no.
What have I drawn?
A parallelogram.
2 vectors getting added.
Well, that would be the diagonal.
Yeah.
Okay. I have drawn a parallelogram. How do we find the area of a parallelogram?
It's not
Okay.
Yeah, okay.
Now, technically, this would be the height, right?
Yeah.
Okay.
This
It's
is
also like a
sine.
projector.
That is the angle in between.
These
So our base, we can say, all right, well, that's the magnitude of u. Our height,
magnitude of these.
oh,
Hey.
which is really just,
Your magnitude of u times v.
U cross V.
U cross v.
so if we want the area of a parallelogram, we can figure it, if we know the two adjacent sides, we can use the cross product to get the area. So my parallelogram has adjacent sides as vectors 2, 3, -5, and 1, -2, 3. So to find its area, we need to take the cross product and then find the magnitude. So let's first take the cross product.
Did we already do?
Yeah, those are the same numbers.
Oh, are they? That's convenient.
Thanks.
Wow. So 111.7.
Well, -1, right?
No, yeah.
-11, -7. So that's our cross product.
171.
The magnitude of u cross v is square root of 171. So that
Units cubed. Squared.
squared, talking about area, so square units, that would be our area.
It's a cubic. Confusing.
It's a cube.
Okay, so here is a riddle for you. If we take the dot product of two vectors, we get a,
Scalar.
okay. If we take the dot product of three vectors, you would get a vector. If we take the cross product of two vectors, we get a
Scalar.
If we take the cross product of three vectors, we get a scalar. Okay. Well,
I'm just getting
we
happy.
would get a vector.
It'd be vector, vector.
Not the riddle that you thought it was it?
You tricked me.
How Can we use a cross product to get a vector? Not by a scalar.
You mean, how do we use a cross product to get a vector?
How do we get a cross product? How do we use a cross product to get a scalar?
Now it's makes sense.
That again. Sorry.
Using a dot product.
Okay. Triple scalar product.
Oh, that sounds all kinds of fun.
Triple integral Shakespeare.
U dot V cross W. Now, yeah, we can take the cross product and then take the dot product. Or
You could do it all at once.
we could. Do it all at once. Put it in a 3x3 determinant as U, V, W.
Just the matrices on the calculator.
Yeah, we can use a calculator properties.
I don't know.
That's yes.
That's gonna get worse.
That's it, no, that's definitely.
What do you get?
Cross products that
Good thing this is
never
the
give you.
At what level of math do they just let you have your calculator whenever? They say like, this is all just so difficult, you can keep your calculator.
I don't know, I'm not sure how much your calculator can help you with theory or numbers.
Yeah, you get to a point where your calculator's not helpful. Okay?
When you
Now, in computational classes, it depends. My Calc 3 teacher did not let us use a calculator ever. Ever.
Alright.
But that was my teacher. Okay? But I imagine in your engineering classes, you'll get to use your calculator. Physics, you'll get to use your calculator. But if you go like the pure mathematics route, like number theory and graph theory and all sorts of kinds of theories, abstract algebra, your calculator does it.
You're no longer doing math in traditional.
Okay, so U dot V cross W. That is a V, I promise.
Oh, wow. Dividing D61 by 64. Go to the second matrix.
Please don't use your calculator. Let's just do this by hand. It really doesn't. Okay? Especially when we have zeros. What's this product?
0.
Plus. Plus. Minus. Plus. Plus. Okay, now, how can this be useful?
Yeah, if you multiply by -1 and then subtract it.
Okay, I want to find the volume of a basically a 3D parallelogram.
Parallelogram. Like the type of pickled peppers.
I don't know.
There's only one.
Okay, please just bear with me here.
burning.
Yeah,
It's like that one
parallel.
It's like that one
I give
parallel.
you MC Escher.
It's like that one painting with the stairs that never done.
Can you kind of see it?
I
Yeah,
see
sort
the
of. It's like the leaning tower.
I see the
Okay.
internet image.
How do we find the volume of a 3D figure?
Length times width times height.
Yeah.
Okay. Length times width times height. Or area of the base times the height.
Yeah.
Okay, so if this is, let me get all these labeled. If this is V, this is W, and this is U. What is the area of our base?
V cross product, magnitude of
Cross
cross product of VW.
And then we need to multiply by the height. How do we figure out the height?
Take the magnitude of U. No, just kidding. It'd be the. Oh, we need the. We need what we did yesterday.
What?
Vector view onto it. Oh, okay.
So we want the projection basically of the base, of the U onto the base.
So cross product represents a plane. Is that right?
Oh, the area.
A cross product represents a vector.
Okay.
What's true about V cross W? It is a vector that is what compared to V and W?
Orthogonal.
Orthogonal. Which means what? Perpendicular. So if V cross W is perpendicular to the base, and we project U onto that perpendicular vector, you get the height. Okay, can you envision what I'm trying to picture to describe here? Okay. Then if we take the magnitude, then you get the length of that vector. Okay, so V cross W, perpendicular to the base. We take our leaning vector U, we project it onto that perpendicular vector, and that gives us the height once we find its magnitude. So, can't spell. To find the volume, we're going to take the magnitude of V cross W times the magnitude of the projection. Okay, now, how do we calculate the projection of U onto V cross W?
U dot V cross W over the magnitude of V cross W squared times V cross W.
Hold on. The dot product over
Magnitude squared times the vector.
times vector U.
Yeah, that checks out.
Okay.
Wow.
That is that times vector U?
So basically,
No.
There's not vector V cross product W.
Yeah, it's times V cross W.
I was gonna say that wasn't any.
Oh, and they cancel it?
Yeah.
And shouldn't V cross W be on the inside?
Oh yeah, good point. So we are left with U dot V cross W inside of the magnitude bars. But since this is just going to be a number, we just worry about its absolute value. So essentially, the absolute value of the triple scalar product will give us the volume of this 3D parallel figure.
How do you simplify that?
You have one V cross W on the outside, you have another on the inside, and so they get squared. So when the squared ones cancel out, we'll just put them out.
So since these are all in magnitude bars,
Yeah,
we can put all of them in there.
right.
So this and this cancels out with both of these.
But the V cross W, but they're, yeah, the Z cross W times Z cross W is not the same as V cross, it's the magnitude of V cross W.
What is it?
There's magnitude lines.
They're all
around-
magnitude.
They're all magnitudes though. Because they're all inside of magnitude.
Oh,
You
so
could,
the V cross W is actually a magnitude, not.
Yep,
Even though
it's in magnitude.
Because it'd be even if you multiplied it all out, it'd be much bigger, but it'd be a magnitude that was just a good number.
you could rewrite it as.
it's.
Basically, these magnitude bars get applied to everything,
Okay,
Got it.
right?
that's confusing.
So you're taking the magnitude of the magnitude of
That
cross
gives the
W.
magnitude.
Yeah.
So essentially, we're left with a triple scalar product. The triple scalar product gives us a number. So the absolute value of that number is our volume. Okay. Now, instead of doing an example, I want to talk a little bit of physics, just a little bit. Okay? What did you use?
No, it's absolute value.
What do you use the right-hand rule for?
Magnitude.
What else?
Electron movement.
Anything else?
Magnetic field.
Anything else?
Electric torque.
Torque.
Oh, yeah.
That's what I was going for.
We don't talk about that much.
Yeah, we do.
Oh,
We use
really?
Vectors for work.
Yeah.
Now we're using vectors for work.
Like you mentioned, very minute, we only went over it, I believe.
Yeah, it is. We talked about it in my class.
Because the force is in. Force is in.
Yeah.
So you guys don't talk about torque very much?
In physics one.
Dude, we don't talk about how it's.
Yeah, we talked about it a little bit in physics one, but
Okay.
we didn't even mention.
So actually, I'm gonna have you. Oh, you guys don't have your books. Okay.
Okay, so that's the
Force directed velocity.
No, it's four. One is force, the other is
For length.
your force length, and I guess is
Moment.
Oh, this is all your hours.
your axis. So torque is going to be on the axis.
Force.
Yeah.
Yeah, axis force.
Wait. Force. Length.
Maybe.
How you doing, Sean?
We really going to do life.
Okay. Torque with vectors with calculus. Okay. So torque, the moment m of a force F about a point P. Okay. The magnitude of the moment m measures the tendency of the vector PQ to rotate counterclockwise about the axis directed along the vector m. M is then the cross product of PQ and F.
What is Q?
So Q is giving you your vector, PQ, which is the direction of.
This is a much more complicated way to just explain the concept.
Are P and Q two different points, and then PQ is the vector between them?
Mhm.
Got it.
and your axis.
Yes.
Yeah.
And letter P is your axis.
Yeah, your axle or your axis of rotation is P. Okay. And then
Okay.
Oh,
There's
oh no, what's happening?
oh no.
What?
Okay.
not good.
Huh?
Leave on the shade. Whatever that was shade.
It's not. That's just a reminder from my calendar.
It looks shady.
Calendar.
It had five
Don't
letters
do
out
that.
P.
Don't read it. A vertical force of 50 pounds is applied to the end of a 1 foot lever. Okay, so a vertical force, I don't know if we're going to get, we'll get there. A vertical force of 50 pounds is applied to the end.
Wait a second. Pounds.
Yeah,
You want the
of a 1 foot lever. I don't think you're going to have any homework problems like this. I just wanted to relate some physics. Huh?
Been writing.
Okay. Attached to an axle at point P. Find the moment of this force about P when theta is 60 degrees. Okay. So essentially, here's our axis of rotation, and we have a 60-degree angle, right? We have a lever, and then force is being applied downward.
Oh. Okay.
Okay.
Upward. I guess it doesn't matter.
We'll say downward, okay? So let's talk about our vector PQ. How do we write vector PQ? What's its magnitude? 1, and what's its angle? 60 degrees. So, I didn't write it, sorry.
Okay.
Drawing.
That's why I was
Okay, so if we stick with right here, so this is a very horrible drawing. This is our y-axis, this is our d-axis, correct? So if we use that little triangle, we can write PQ, cosine of 60 degrees times J plus the sine of 60 degrees times K. That'll get us that vector in the YZ plane. So our vector is 1/2 J plus radical 3/2 K. And our force is being applied downward, so what is that vector? What is vector F?
0, 0, 0, degree.
Okay, so to find that moment, we're going to take the cross product. Okay, so 0, 1/2, radical 3/2, 0, 0, -50. Okay, I will save you the work. It looks like this is going to be the only diagonal that doesn't have a 0 in it. Okay? So if that's the vector M, then the absolute value of it, or the magnitude, if you will, is 25, and that's our torque. Torque is a measurement of work. No?
Rotational.
Rotation force.
Okay, so Newton meters, and since we're not using newtons or meters, it's foot pounds, which I know you hate.
It's foot dot pound versus. It's one of those weird overlaps.
Okay, I don't think I gave you any of those problems, though. I just wanted to talk about torque and how it can be applied to what we're doing.
Oh, okay, that's the
Yeah.
Here's your homework.
Or not.
Thank you for sticking with me there, physics people.
Bye, Sean.
Bye,
Bye, Sean.
I'm sorry. You're welcome.